Hello and welcome. Today we're going to go through and just explore why evaluating integrals using the fundamental theorem works. And of course, when we ask this question of why, we're really going to go through and do a mathematical proof of it. All right, so to do the proof, I think we just have to start with, let's state what that FTC is. Okay, and again, we know it's actually just the partial definition, the partial FTC, really. There's another whole part of the FTC we haven't talked about yet, but let's just pretend that we're just focused on this fact that we've stated so far. And of course, we know already this is a very powerful fact, and that happens when our capital F of x, and when you take its derivative, it's equal to f of x everywhere on little a all the way to little b, okay? And also, we need f to be continuous. And we, of course, we need that continuity because the integral has to exist. Okay, so that's a fairly weak requirement. It's just a housekeeping requirement, if you will. All right, so we're going to go back to this question of why. Why does this work? Why does somehow taking the antiderivative somehow allow you to find the area under the curve of a function? It doesn't seem like it should be true. It's something that's definitely very curious. It doesn't seem to like all the way line up. It doesn't seem intuitive. But let me see if we can try to figure out a way why this has to work. The way I'm going to start with this is just think about it geometrically, but I'm actually going to highlight one important fact. An important fact used to prove this FTC. And you may remember from previous chapters, we talked about this thing called the mean value theorem. Okay, and the mean value theorem says if you have a capital F of x, for instance, and I have, if I think about it like this, well, actually, I'm gonna undo that. I'll go with yeah, there we go. We have it at a point xi, and we have it at a point xi plus 1, like that. It doesn't matter what points you're really looking at here. And what we have to assume that capital F here has a derivative between xi and xi plus 1. So we're able to compute this. Okay. So the mean value theorem, sometimes we call it the MVT. Okay, so the mean value theorem says there is some CI that's in the interval somewhere, and there actually could be more than one, okay, such that the average slope of the secant line is equal to f prime at ci. All right, let's write that down. So remember the average slope of the secant line. You may recall that from the very beginning of when we started talking about calculus. That, of course, is going to be f of xi plus 1 minus f of xi, all divided by, and now I'll call this delta x there. It'll be delta x, and delta x, I'll call it delta xi even. Delta xi, of course, is equal to xi plus 1 minus x of I. Right? And that is equal to f prime evaluated at some point. So if I was to write this out, I would write that secant line like this. So I'll label it with red. And then I'll say, okay, there's some value, and I think it's right about there. I'll call that Ci there. If I look at the slope of the tangent line at that point, which in this case is going to be f prime of Ci slope, that will be exactly the same number. Okay? That means those two things here are identical. Okay, so this fact will be very important. Okay? And remember, the theorem says there is some Ci. It doesn't say exactly where it is. It just says that it has to be in there somewhere. Okay, so with that fact fresh in our head, now we can go proceed with proving the fundamental theorem. So let's go to a new page. And recall, we're going to start with our favorite thing, of course, the integral. So this is going to be our proof. And we're going to write it out like we always do as the limit of finite sums going to infinity. Okay, and we know, of course, that the function goes like this, and we're going to break it up into these pieces. There'll be an xi and an xi plus 1, and so on, like that. Okay? All right, so, but we also know that f of x is the antiderivative. And we know that capital F of x is that antiderivative. So I can write f prime of x is equal to little f of x. Right, so let's also point out an important thing here. This area under the curve, we can choose any representative point. Inside each subinterval. So representative point, so I'll call that xi star, okay? And the subinterval is going to be x of I to x of I plus 1, okay? All right, sorry, I think I made a little mistake here. I need to just put an n up there on the top there. There we go. Okay, good. So with this all put together like this, what we can say is we can put that inside. And it's really important that we're talking about the fact that it could be any point inside there. And so I'll even write that down. We can put our xi star anywhere we like. Okay? It could be on the very far end. It could be any point in there. So maybe I'll write that a little bit bigger. That one's okay. This is okay too. In fact, any point along here, on any single one of them would be fine to do it with. Because we know, of course, the delta xi's are always going to get smaller and smaller and smaller. The walls will just close in until there's very little leeway either way. Okay? All right, so there we go. We've kind of written all of our stuff out there. So what we can do is now use our fact and then rewrite it as limit n goes to infinity of the sum of I goes from 1 to n, but now we put f prime of xi star times delta xi in there. Okay? All I've done is replaced it based on the definition of what the antiderivative is. The idea that we take the antiderivative, we get little f. Okay, so we've done not very much so far. The next thing we're going to do, though, is go note, and I'll write this in a different color. The mean value theorem says that there is a specific CI, I'll call it, such that f prime of CI is going to equal the average slope of the secant line. In this case, it's going to be f at xi plus 1 minus f of xi all over delta xi. So anywhere I see one of these, I can put one of these in its place, right? So what we're going to do is choose our xi star to be equal to that special ci, okay? And we can do that choice because, again, when I said any, I meant any. And the mean value theorem says that ci exists. It will always be in there somewhere. So it's not only something that I can choose, it's a thing I know that I can always choose. All right, so that gives us the next part of our equation, or the next step in our process. We have limit of n goes to infinity of the sum I equals 1 up to n, and now we write f of xi plus 1, okay, minus f of xi all over delta xi times delta xi. Well, this is really convenient or odd, but those are, of course, going to cancel. And what are we going to get out of it then, of course, is the following. Now, if we look at this carefully, what we're going to see then, of course, is we're going to have, well, I'll just write it out simply here. Oops. Limit as n goes to infinity of the sum I equals 1 to n. We're going to have an f of xi plus 1 minus f of xi. So this is a very, very odd summation. Because remember, we're integrating from x1 all the way to xn here, and we're doing some sort of partition. So there's going to be an f of x1. And of course, x1, of course, is going to be a, and xn is going to be b. So I can actually write that in there. I'll just call that a. Then we have x of x2, f of x3, f of x4, and so on. And what we're going to get out of this is what we're going to, so I'm going to actually write down one of the first terms. We're going to have f of x2 minus f of a. That'll be the first term. And the second term is going to be f of x3 minus f of x2. That'll be the second term, plus f of x4 minus f of x3. And we're going to keep going until we get to f of b minus f of n minus 1. Oops. Let me write that more carefully. All right, and we can see here by looking at this very, very long sum is that x2, that's going to cancel with that x2. The x3, that'll cancel with that x3. The x4, that'll cancel all that stuff, and this will cancel, and there'll be two terms. There'll be an f of b and a minus f of a. Those are the only two terms that don't cancel. All right. We just have to remember one thing in that summation there, which is we still have that limit, n goes to infinity. Of course, there's nothing there. There's no n involved anymore. So we have f of b minus f of a, which gets us exactly where we needed, exactly where we wanted to find ourselves. All right, so this then is a direct proof that the integral from a to b of little f of x dx is going to be equal to the difference of the antiderivatives at the end of the interval. All right, I hope that was helpful to see this proof done fully out. I will stop there, and we'll carry on in learning more about the fundamental theorem in later videos.